Hello viewers, in this tutorial we are going to discuss about transient response of first order circuit. So let me give a brief description about transient analysis. In the network theory subject, we have to deal with three basic elements, namely resistors, inductors and capacitors. Out of these three elements, resistors are static elements in the sense that voltage across the resistor or current through it doesn't depend on time, whereas inductor and capacitors are dynamic elements in the sense that voltage or current for inductor and capacitors is dependent on time. Say, for example, current flowing through the capacitor is given by IC equal to C into dV/dt. If you look at this expression closely, then you will find that the current flowing through the capacitor and voltage across the capacitor are both function of time. So they are dynamic. In transient analysis, also called time domain analysis, computes the circuit's response as a function of time. By circuit's response, I mean variation of voltage and current levels with respect to time. So, in transient analysis, there should be at least one dynamic element, that is inductor or capacitor. We don't carry out transient analysis for resistive network, which play a very important role in transient analysis to study the charging and discharging of an inductor or capacitor. So, transient analysis is also called as switching analysis. Let us consider a RC circuit consisting of a series combination of resistor, capacitor excited by a DC source. Here S represents a switch which is closed at t equal to 0. When the DC source is suddenly applied to the RC circuit with the help of this switch, the voltage or the current can be modeled as a step function, and the response is known as a step response. We know the unit step function given as u of t equal to 0 for negative values of time and 1 for positive values of time. The function is undefined at t equals to 0, where it abruptly increases from 0 to 1. This figure shows that a step voltage is equivalent to DC voltage source with a switch. If you analyze these two figures, for t less than 0, the voltage across AB for both the figures will be 0, and for t greater than 0, the voltage across AB will be V0. Now the circuit's response, that is voltage across the capacitor, can be found by applying Kirchhoff's law in the RC circuit, which will result a differential equation of first order. Hence, this RC circuit is called as first order circuit. This differential equation need to be solved by variable separation method to obtain the final result. Rather than going through this long process, we will follow a systematic approach, or rather a shortcut method for finding the step response of an RC circuit. The complete response or total response of the circuit can be decomposed in two ways. In terms of source of response, we can break it into natural response and forced response. The natural response refers to the behavior of the circuit with no external source of excitation. It eventually dies out along with the transient component of the forced response, leaving only the steady state component of the forced response. Whereas the forced response is produced by the circuit when an external source is applied to the circuit. In terms of permanency of the response, it can be broken into transient response and steady state response. The transient response decays to zero as time approaches infinity. Steady state response is the behavior of the circuit a long time after an external excitation is applied. This figure shows the time frame for transient analysis ranging from t equals to minus infinity to t equals to plus infinity. Here we have assumed that the switching has been done at t equals to 0, which is represented by this vertical axis. For utilizing the shortcut method to obtain the complete response, we will analyze the circuit for 3 different time durations. For t less than 0, the circuit will be in steady state. The circuit will be analyzed during this period to find the initial condition or the initial charge stored across the inductor or capacitor. For t greater than equal to 0, the circuit will be in transient state. The circuit will be analyzed during this period to find the value of time constant, denoted by lowercase letter tau. It indicates the rapidity with which the voltage or current changes. At t equals to infinity, the circuit will again be in the steady state. At this time of the time frame, the circuit will be analyzed to find the final value of the voltage or current of the inductor or capacitor. So, in the full range of this time frame, steady state comes 2 times. One during t less than 0 and other at t equals to infinity. Also, you need to remember that at steady state, capacitor acts as open circuit and inductor acts as short circuit. Whichever way we look at, the complete response for step input excitation is given by this equation, where x of 0 is the initial value and x of infinity is the final value. If the analysis is such that the switch changes its position at different instant of time instead of t equals to 0, then the response will be modified as shown. You need to remember that the equations are valid when input excitation is constant. Secondly, the time constant of the circuit should be a finite value. Thirdly, the circuit should be of first order. And finally, when capacitor follows its property that it doesn't allow the sudden change in voltage across it. Now, let us solve the circuit theoretically using shortcut method before actually implementing it on Multisim software. As discussed, let us analyze the circuit for t less than 0. We know for t less than 0, ut equals to 0. So, current flowing through the capacitor or the loop current is 0. Hence, voltage drop across the capacitor will be equal to 0. And by capacitor property, voltage across the capacitor just before switching should be equal to voltage across the capacitor immediately after switching. Thus, the initial condition has been obtained. In the second part of our analysis, we will calculate the time constant for the circuit. For t greater than equals to 0, ut equals to 1, and we will have a current flowing through this loop. For first order RC circuit, time constant is given by R multiplied by C. In finding the time constant, R is often the Thevenin's equivalent resistance at the terminals of the capacitor. That is, we take out the capacitor C and find RTH at its terminal. If we have more than one capacitor, but capacitors are arranged such that we can find its equivalent capacitance by series parallel combinations, but not of second order. Then we take the equivalent capacitance and multiply with R to get the time constant for the circuit. Now, for this circuit, to find the Thevenin's equivalent across the capacitor, first of all, this capacitor will be taken out. Then, independent voltage source will be short circuited, and we'll remove these ground connections. Then the circuit will look like as shown. So RTH will be equal to 1 kilo ohm. By using the formula tau equals to R into C, the time constant will be equal to 10 milliseconds. From this value, we can also find the settling time denoted by T settle, which is equal to 5 times the time constant. The settling time can be defined as the time required for the circuit to reach its final state or steady state with an error less than 2%. You need to remember that in network theory subject, we take the settling time to be equal to 5 times of time constant. Whereas in control system subject, we take the settling time to be 4 times of time constant. In the third part of the analysis, that is at t equals to infinity, we will calculate the final value of the response. At t equals to infinity, the circuit will be at steady state. So the capacitor will act as an open circuit. So no current will be flowing through this circuit. And the drop across this resistor will be 0. And whole source voltage will be dropping across the capacitor. Therefore, the Vc of infinity will be equal to 10 volt. Now, by using the formula for complete response and substituting the values for initial value, final value and time constant, we will get this expression for voltage across the capacitor. Once the capacitor voltage is obtained, the capacitor current can be easily obtained by using the expression IC equals to C into dVdt. If we try to draw the graphs for voltage across the capacitor and current flowing through it, the corresponding graphs will be as shown. Now we are in a position to simulate the circuit and verify the result obtained by this theoretical calculation. So this is the Multisim software interface, and I have already formed the RC circuit with its respective values. Let me show you how I have set the parameters for the step voltage. So double click on it, go to the value tab in this component property dialog box. First parameter is the initial signal level. I have set it to 0. The signal after the step, that is the final level, is set to 10 volt. The duration of the step is set to 0 seconds. Since I don't want any delay in the signal, I have set the output rise or fall time to a value as low as possible. Then press OK. For carrying out the transient analysis, go to Simulate tab, select Analysis and Simulation. Select Transient Analysis. Let me explain how to configure Transient Analysis in Multisim. You can find 4 options on the initial condition parameter. Select Set to 0 if you want to start your analysis from 0 initial condition. Select User Defined if you want to start your analysis from initial conditions as set by you. Say, for example, if you want to define the initial voltage stored across the capacitor, you can double click on the capacitor and set the initial condition or the initial voltage stored across the capacitor here. Select Calculate DC operating point if you want the Multisim to first calculate the DC operating point for the circuit, then use that result as the initial conditions of the transient analysis. If you select determine automatically, then Multisim tries to start the simulation using the DC operating point as the initial condition. If the simulation fails, it uses user-defined initial condition. So for my analysis, I will select set to 0, since I want my analysis to start from 0 initial condition. Next, set a start time of the transient analysis. That must be greater than or equal to 0 and less than end time. After that, set end time of the transient analysis. I will set it to be 0.1 seconds or 100 milliseconds. Now you can set the maximum time step the simulation can handle. Multisim says that the smaller the step size, more will be the accuracy at the cost of simulation time. That is, your simulation time will increase. I will keep it as determined automatically. You can set a time interval for simulation output and graphing by this parameter. I will keep it as determined automatically. Next, go to Output tab. From this list of variables in the circuit, select V3, which represents the voltage across the capacitor. Click on Add and run the simulation. The grapher window opens up. Let me select a light background by clicking on this tab. In this graph, the vertical axis corresponds to the voltage across the capacitor in volts, and the horizontal axis corresponds to the time axis in seconds. I will select the grid view so that the coordinate points are easily readable. Let me select the cursor, then click on Show Cursor. You will get two cursors over here. Now, if I compare this graph with the theoretical calculation, you will see that the maximum or the final value of the graph is 10 volt, which is same as the theoretical value. Again, according to the definition of time constant for the standard charging equation, it is the time required for the response to reach 63.2% of its final value. And for our case, the time constant is 10 milliseconds. So, if we check the corresponding value in the graph, it should be equal to 63.2% of maximum value, that is 10. So 63.2% of 10, that is equals to 6.3 volt. So let us move the cursor to t equals to 10 milliseconds, that is your time constant, and check the corresponding value of the graph. So as you can see, the x2 value represents your time and y2 value represents the corresponding voltage. So when time equals to 10 milliseconds, then your voltage is 6.3 volts, that is 63.2% of its final value. Also, the settling time, which is equal to 5 times the time constant, is equal to 50 milliseconds. So its corresponding value should be more than 98% of the final value, that is more than 9.8. So let us verify the settling time constant from this graph by setting this cursor to a time equal to 50 milliseconds, that is your settling time. You can see the corresponding value of the voltage is 9.9 volts, which is greater than 98% of the final value. So you can verify all those theoretical results with the simulation result. Now let me quickly show you the graph for the capacitor current. So similarly, you need to select the current flowing through the capacitor and run the simulation. So you can see that current through the capacitor graph for the RC circuit is a discharging graph with its initial value of 10 milliampere and finally it settles down to 0 at infinite time. Similarly, if I define the time constant for a standard discharging case, it is the time required for the response to decay to a factor of 36.8% of its initial value. So if I set the cursor to 10 milliseconds, which is equal to the time constant for our case, then the corresponding value of the current should be equal to 3.6 milliampere. Thus, we have verified the simulation results with the values obtained by theoretical calculations. If the same analysis is done for a RL circuit, what would be the nature of current flowing through the inductor? That can be denoted by IL of t. And what would be the nature of voltage across the inductor, which can be denoted by VL of t. So which of these will be a charging graph and which one will be a discharging graph? You can leave a comment below. So that's all for today. Thank you.